everyone, thank you so much for joining me for this lesson. We're going to be learning about electronegativity and bond polarity. So electronegativity is the ability of an atom to attract the bonding electrons in a covalent bond. And we're also going to be interpreting the Pauling electronegativity values. We're also going to explain a polar bond and permanent dipole within molecules, and a polar molecule and overall dipole in terms of permanent dipoles and molecular shape. So firstly, we're going to define electronegativity, and it's the power of an atom to attract a pair of electrons in a covalent bond towards itself. So basically what it means is that when two atoms are covalently bonded together, electronegativity is how much one of the atoms attracts the electrons in the covalent bond towards itself and away from the other one. And there are three factors which affect electronegativity. The first one is nuclear charge. And if there's a high nuclear charge, this means there's more protons, which means there's a stronger attraction between the nucleus and the bonding pair of electrons, which it's wanting to attract. So that means that when we have a higher nuclear charge, that is equal to more electronegativity. The second factor is atomic radius. Now, when atomic radius is bigger, meaning that there's more space between the nucleus and the outer electrons, there's less of an attraction between the nucleus and the bonding pair of electrons, so it can't attract them as well because they're further away. So that means that if we have a bigger atomic radius, then we have, it is less electronegative. And then the third factor is shielding. So when there's more shielding, that means that the attraction felt between the bonding pair of electrons and the positive nucleus is less because there's more things in the way. So when we have more shielding, then we have less electronegativity again. So when we look at the periodic table, we know that nuclear charge increases along the period, and atomic radius increases down a group, and shielding also increases down a group. So then we can say that electronegativity actually increases along a period, and electronegativity decreases down a group because the atoms are getting bigger, so the electronegativity decreases, and along a period the nuclear charge increases, so electronegativity increases. And so this means that these atoms here are actually the most electronegative. One thing to note is that we don't include the noble gases here because they already have a full outer shell, so they don't form covalent bonds. Next, we're going to have a look at electron density, and this is just basically where the electrons are more focused between the two atoms. So polarity is about the unequal sharing of the electrons between atoms that are bonded together covalently. So there's two things that can happen. So first thing is that if the atoms are the same, then the electrons are shared equally between the two atoms because they've got the same electronegativity. So their ability to attract the electrons is the same. So that means the electron density is very uniform throughout, for example, with 2 fluorine atoms. And so the bond is non-polar, meaning there is an equal sharing of electrons. The second thing which can happen is covalent bonding between different atoms. And because they're different atoms, it means that they automatically have different electronegativities. In this example, fluorine is much more electronegative than hydrogen, so the electrons are more gathered around the fluorine because fluorine's ability to attract the electrons is much larger, hence a bigger electronegative value. So we say that the electrons are distorted towards the fluorine. And this makes the bond polar because there's an unequal sharing of the electrons. And we use partial positive and partial negative signs to indicate which is more electronegative. The signs are delta plus and delta minus. Delta is a Greek letter. And so a permanent dipole is formed, which just means a permanent difference in the electronegativity and like how the electrons are placed. So in this example, the electrons are all crowded around the fluorine, so that becomes the partial negative, and hydrogen becomes the partial positive. And the rule is that if there's a greater difference in electronegativity, then it is more polar because there's a bigger unequal sharing of the electrons. Now on to some questions. So the first question says, explain why fluorine is more electronegative than chlorine. So after looking at the periodic table, fluorine is in group 7 and in period 2. And chlorine is also in group 7 and in period 3. Now we know that atoms gain more electron shells going down the groups, sorry. So that means that chlorine has an extra shell than fluorine. So fluorine has 2 shells and chlorine has 3 shells. And so because they both form 1- ions, so we have F- and Cl-, then we just look at the size. And because fluorine is a lot smaller, that means that the atomic radius is smaller and the bonding pair of electrons are closer to the positive nucleus. So it is more electronegative because the power of it to attract the pair of electrons is bigger because it's closer to the electrons compared to in chlorine when there's more shielding and because it's further away. For number 2, work out these molecules have permanent dipoles: water, ammonia, and boron trifluoride. So in order for molecules to have permanent dipoles, there must be an unequal sharing of electrons throughout the molecule, not just if they have polar bonds. So molecules can have polar bonds, but not be polar as a molecule. So for A, for water, water looks like this. And oxygen is much more electronegative than hydrogen, so that becomes the delta negative, and these two become the delta positives. And so we see that these bonds are definitely polar because we've got a more partially positive atom and a more partially negative atom. And the bond is also, the molecule is also polar because if we look at the electron density of it, it would look something like this. So there's more electrons over here compared to here and here. So the whole distribution of electrons around the molecule is not is not equal. So for B, we have ammonia, and ammonia is made up of nitrogen and 3 hydrogens. Again, nitrogen is a lot more electronegative than the hydrogen, so that becomes the delta negative, and then these become the delta positives. So for sure, the bonds are polar, and the molecule is also polar because, again, there's more electrons gathered around the nitrogen compared to the hydrogens. So the distribution of electrons is uneven. And then for C, we have boron trifluoride. And that means that we have boron and 3 fluorines. Now, fluorine is definitely the most electronegative compared to boron, and so those are the partially negative atoms, and boron is the partially positive. However, because of the placement, because there's 3 fluorines attached to a central boron, this means that the bonds may be polar, but the whole molecule itself does not have a permanent dipole and is not polar, because if we had a look at it, the electron distribution would be quite even because they would be gathered around the fluorines, but there's 3 of them around a boron, so that would be quite equal. So this molecule would not have any permanent dipoles. Would not have any permanent dipoles, but these 2 would. Hi everyone, thanks so much for joining for this video. Today we're going to look at a harder question for the topic of, what is the topic? Bond polarity. Hi everyone, thanks so much for joining for this video. We're going to look at a harder question for the topic of bond polarity. So the question asks, using the compounds CHCl3 and CCl4 as examples, explain the difference between a polar bond and a polar compound. So for CHCl3, we have a carbon and then 3 chlorines and a hydrogen. And so when we draw it out, it should look like this. And then chlorines. So the chlorines each share an electron. So then they have 6 left in their shells. And then we have the carbon electrons, and then obviously the hydrogen as well. And that's how it's bonded. So it has 4 bonding pairs and 0 lone pairs. So we know that this forms a molecule that looks like this. And now we can have a look at the electronegativity of it. So chlorine is definitely the most electronegative as it's a lot smaller and it has a higher nuclear charge. Carbon is kind of in the middle, and hydrogen is definitely the least electronegative. So that's why we give chlorine the delta negatives and hydrogen gets the partially positive charge. And so after that, we now look at the electron density of it. So because chlorine has the higher electronegativity, that means it's got a higher attraction to the bonding pair of electrons. That means that lots of electrons are gathered around here, where the chlorines are. And then with the hydrogen, there's not many. There's only a few. And so because of this, there's a lot more electrons around the chlorine. And so this compound is actually polar. So this is a polar compound. And because there's a difference in electronegativity between one of the atoms and the other atom that it's bonded with, for all of these bonds, that means that it has polar bonds as well. So it has both. Now we're going to look at CCl4. So you've got the carbon again with the 4 electrons. And then we're going to bond it with 4 chlorines. 3, 4. And they're going to share 1 pair of electrons each. And there's 6 left in each of their outer shells. And so again, it has 4 bonding pairs and 0 lone pairs. So the shape it creates is the tetrahedral. So it has carbon and then chlorine, another chlorine, chlorine behind, and a chlorine over here as well. And now we have a look at the charges. So chlorine is much more electronegative than carbon. So we give that the delta negative. So these are all delta negatives. And the carbon is delta positive. And now we have a think about electron density. So electrons will be much more attracted to the chlorines compared to the carbons. But this is the case for all of the chlorines. So that means that the overall distribution of electrons throughout the whole compound is actually quite even because there's 4 chlorines which are surrounding the carbon. So that means that we have a nonpolar compound because there's no overall unevenness in the electron density and how the electrons are moving about in place. But because there's a difference in the electronegativity between 2 of the atoms which are bonded together, in this case we only have 1 type of bond, a C to a Cl, then that means we have polar bonds because the chlorine is much more electronegative than the carbons. So as you can see from this question, both of these molecules form tetrahedral shapes because they have 4 bonding pairs, but because of the electronegativity of chlorine compared to hydrogen, one of these compounds is polar and the other compound is not polar, even though they both have polar bonds. So it's really important to remember that even though you have polar bonds, sometimes the whole compound is not polar, depending on whether the electrons are distributed evenly or not.